Welcome back. So first of all, I would like to say sorry to everyone that it's been some time. I think it's been almost 2 months that I haven't posted any video. So I'm sorry for that. And so now today we'll be continuing on learning the product design and development course or lecture series that we started learning on top of that. And today specifically we will be looking into prototyping. Now just to repeat, we are an academic researchers community predominantly, but there would be a lot of viewers from industry backgrounds and entrepreneurship backgrounds, so they will also help from these videos. But mostly we would try to understand. So as you can see, of course, product design and development, this itself is a industrial or some sort of an more of an topic which is relevant to people from industry who are building new products and entrepreneurs, etc. But we are trying to learn these concepts from an academic point of view, and how academic researchers can use this concept to improve their research or improve their track record of research, and building up to something more interesting and improve or enhance their career in terms of paper, patents, and then funding, etc. So that is more or less the goal of this lecture series, if just to repeat. And yeah, so let's then get started. Okay, so as we know, in this lecture series, basically each chapter starts with basically author gives the particular example, and from that example, the concepts are basically explained in context to that example, to make the reading more easy. They use this particular example. So for this particular chapter, they use this particular product called iRobot PackBot. So basically it's a the iRobot PackBot line of tactical mobile robots was designed by iRobot Corporation, and it is right now part of a new different company called Teledyne FLIR. Sorry, I don't know the pronunciation right, but anyway. And yeah, so this products assist law enforcement and military personnel to conduct operation in dangerous environment. For example, PackBot robots were used to help search for survivors in the wreckage of the World Trade Center in September 2001, and were the first robots to enter damaged Fukushima nuclear power plant after the 2011 earthquake and tsunami. The mobile chassis of the PackBot accepts a wide range of payloads, including a robotic arm that can be fitted with a gripper, video camera, lighting, acoustic sensors, chemical and radiation detectors, or specialized equipment such as that needed for disarming bombs. So that is the product that would be used for today's learning on the chapter based on prototyping. Now, what is in prototyping? Of course, the name itself, we know that what is prototyping in a general sense, but why we are as an academic community are interested into prototyping, because if you are in researchers in application science, so in the end of the day, your research is based on some method. You are developing some method or some hardware, software, etc. But that is part of something much bigger. So in the end of the day, it's basically you are actually assisting into development of some product actually, unless you are very fundamental researchers working in some fundamental level of science. So that is also okay, but I think we can also argue that in that also you can always use this concept, that certain fundamental models and how. So the prototyping, what I'm trying to mean is that prototyping itself is a concept that has to be used in our academic domain also, in a sense that when we work on certain projects, a lot of time we build the toy model of the actual method that we are proposing, because the actual method is very complex and computationally expensive. So it is not easy to run various sort of simulation or specifically or maybe in an experimental setting, build everything from everything in the first day, because it's a very expensive thing. It's not possible to build everything, what I mean. So the prototyping is always a very interesting concept for academic researchers also. If we are working in a method development, that means which is basically can be part of a software development, there also you realize that your particular method that you are proposing is quite complex and computationally expensive. So you want to build on toy model, so that's also example of prototype. But if you are, let's say an experimental researcher, so there you are working on some new geometry of the detector, let's say, but we know that we all start with some prototype like single module detector, experiment on performance, this, that, etc., and try to infer that how when we scale up whether it will work or not. In that case also we always work with some digital twin, that means we work with some simulation model, because there you can study with less expense. Less means relatively nothing, you don't have to spend run simulation, you don't have to spend too much. Whereas if you try to think that okay, from day one, or I will buy all the equipments, and so that is not feasible, because expensive, and also you need human resources. You might not have the number of students or number of engineers in your lab to build that on that for day one actually. So we understand that the prototyping as a concept is very important for our academic researchers also. So that's why we think this is an important topic to understand. Not just and of course, if you are from industry background, of course you can take this lecture as a general information, and you can help from it. But so let's get started. Let's move ahead. Now before we start, let's see the formal definition of a prototype. And the author basically said here that we define prototype as an approximation of the product along one or more dimension of interest. So that is more of very general definition, and that's exactly that we want. And we'll see the content of this lecture. There you will see that how this definition is more suitable. This definition deviates from standard usage in that it includes such diverse form of prototypes as concept sketch, mathematical model, simulations, test component, and fully functional pre-production version of the product. Now let's see first of all what are the type of prototype one can see. How can you divide different type of prototype? Like as a word, when you hear the prototype, then you see that okay, so it's like some sort of version, but then it is good to have a more deeper or more detailed knowledge about it. So one can divide the type of prototype in two dimensions. One is whether it is how much it is physical versus how much is analytic, and another dimension is how much it is comprehensive versus how much it is focused. Now we will explain step by step. First of all, we'll explain what is the physical prototype is. So here in the figure you can see physical prototype basically so in figure you can see the 3 physical prototype. An example of physical prototype include models that look and feel like product, proof of concept prototypes used to test an idea quickly, and experimental hardware used to validate functionality of the product. So for example, here you can see that the for customer approval you might want a full, or at least a prototype which looks like the original final design or final form of the product is, because they like to see how it looks also. That's also matter. Maybe it's not so important in this case, but if it is a different kind of product, ergonomics and the aesthetics also going to be important. Now let's consider another form of prototype which will be, that's why I was thinking like we should have a lecture video on this part, on this chapter, and here you will understand that let's say you want to test the wheel, so for creep testing so you make a different design of the wheel itself without the actual total robot design. You just focus on the wheel and you do certain type of testing which is formalized in some engineering discipline, that this is how we test things, etc. So that is also considered as a physical prototype. So now we understand that prototype is a very diverse concept, and again, now from an academic researcher's point of view, you understand that okay, so I want to work with this is my bigger goal of research, but then you try to focus maybe for 6 months, 1 year, this is what I want to gain, and so you are focusing on subsystem, and that's also prototype actually, and of course the integration of that into the whole bigger picture, that itself takes time, and that's you can see at a product development point of view. So again it raises the point that why I'm doing these videos, that because I feel like as an academic researchers we can take motivation of these things and incorporate into our daily or bigger level planning. And finally, third physical prototype here it's shown is in the below figure, the sand test of complete system. And so they are also you can see from the word itself, sand test, you can see in the figure also. What I'm trying to mean here, that each prototype doesn't mean that it's the full form product. Even for the customer approval, maybe the importance is how does it look, although I can't say specifically in this case, but in some product customer approval is more like how does it look, or how does it will perform the task, etc. And for sand test, maybe it is just you don't need the software, you don't know the payload, etc. Maybe not that important. So what I mean is, prototype doesn't mean that it has to be the full form of product. And so it's not like that you develop the product and get the one version of it and that's the prototype. It's more like it can be carved out in the various phases of the product development, and you just create a derivative version of it, and based on what exactly the testing or what are the purpose, whether you want to show it to the customer, whether you want to test certain parameter of the certain capability of the product, etc. So depending on that, prototype can be different actually. So that's what I mean. Now, more important thing here, so as I said that the second type of prototype if you try to divide the prototype in terms of physical versus analytic, is analytic prototype, which is simply speaking is computer simulation. It can be CAD design, it can be mathematical model. Now we see that prototype is now the concept prototype here author is using it as in a very diverse sense, and it should be used as a diverse sense. So CAD design of course is something that most of us know that how important it is, like and I think most of the field in the research now uses some sort of a CAD design. A lot of designs of a lot of software. For example, in detector technology, when you try to develop detectors, they have the specific ability to, you can design your geometry into CAD and you can import it into your software and it will work actually. So CAD is, of course, is the famous thing, and it's been, I think, here there in the field, or in the in the field for, like, I think from 1990s I think it was started. But anyway, and of course, you see we saw that in the previous slide also, the wheel testing. So that is more like a physically you build something, but here in the simulation also you can build a certain geometry of the wheel, and then there is something called finite element testing. There also you can test certain performance, how it will work or not. And yeah, and finally dynamic simulation model. So exactly I don't know what that mean, but you can understand that this again some simulation which may be needed to be done to understand certain thing, whether certain design or certain geometry physically in a physical, not physical, but I'm talking about the physics as a subject point of view, physical Newtonian physics will work or not, something like that. So I hope so that's the case, but I don't know specifically. Now, another way of looking at what is the type of prototype that you want is in the form of whether it is a comprehensive prototype or whether it is a focused prototype. So in other words, what I mean is that the comprehensive prototype or focused prototype is not something, we are not talking about something different from physical or analytic prototype, but it's more about different way of dividing the various prototype ideas. So comprehensive prototype basically, okay, let me see, I think I will just read it from the book here. The second dimension is the degree to which a prototype is comprehensive as opposed to focused. Comprehensive prototype implement most, if not all, the attribute of the product. An example of a comprehensive prototype is one given to customers in order to identify any remaining design flaws before committing to production. And in contrast to comprehensive prototype, focused prototype implement one or a few of the attribute of a product. Example of focused prototype include foam models. I don't know exactly what is foam model is, but I think it's more like some, I don't know, maybe using foam to create a physical version of the product maybe. Anyways, to explore the form of a product, and hand-built circuit boards to investigate the electronic performance of a product design. A common practice is to use two or more focused prototypes together to investigate the overall performance of a product. So one of these prototype is often a look-alike prototype, and other is the works like prototype. By building two separate focus prototypes, the team may be able to answer its question much earlier than if it has had to create one integrated comprehensive prototype. So work like means functional point of view, whether the robotic arm will work in a desired way or not, and whether it can maneuver in the rough terrain or not. If the robot is entering into like nuclear disaster areas, the Fukushima example that they had given, then it has to be built in certain, one example of course we know that in Mars rovers, they are built with so much care in the mind that terrain in the Mars, the planet Mars is quite different and can be very challenging, this that. And I think one of the documentary I was seeing that they have the two version of the same robot, and when they see that certain terrains in front of it is very challenging, they try to create a same sort of a challenge, physical environment in their lab with the digital, sorry, not digital version, but the twin other version of the robot, and try to create some solution out of this. So that's also an example of a prototype, that's a very innovative way of using a prototype, and that's like, because they here you can understand that cost and the risk becomes two important factor, and we'll discuss this thing in the later slides. But so it's important to understand look-alike and work-like prototype. So maybe these are not important for academic researchers, but certainly for industry people these are very relevant concept. Now this is a plot, and I think it's better to use understand this concept in a plot. Now you will understand in more detail what this means. So here in this plot, basically you can see different so depending on your need for a particular situation, like, so for example, let's understand what is focused and analytic. When the prototype basically is of more of an analytic form and in more of a focus, then, so I'm talking about the third quadrant. So when the prototype is basically more of a focus type and it's more of an analytic type, so that basically means it is more like a CAD model. So in generally, I will give an example that a lot of cars, and initially the ergonomics of the car, how does it will look like Ferrari or Jaguar or Land Rover, whatever it is. So initially I hope that these are made in a CAD design first, so ergonomics and how aesthetics will look like. So that's more like in prototype in the form of that's also a prototype of the final product. You have to think like in that way, and that's also done in a 3D CAD model. Color rendering, I don't know exactly what it means, and it can be also beam bending equation of wheel spoke geometry, so that's also analytic and focused. Finite element analysis of heat dissipation, math model of motor performance, sorry. So these are examples of so something like prototype which is more focused focused and analytic. Now if it is focused and more physical, because you need physical, because you can't rely on the simulation totally, so we'll discuss that later. So if it is a focused but it is more of a physical, then the example can be like the wheel impact test. So it's more like the next step to take, like where you study the mathematical model in a focused and analytic prototype. Now you want to test it on a physical way. So here also you remain focused, because you are not talking about the whole robot but just the wheel of it. And so basically but then you make it physical version, maybe through 3D printing or whatever the general way, conventional way, and you do the testing. So that must be certain, there must be some engineering discipline where things had been systematized, that this is how we test the wheel, etc. You don't need to build the whole vehicle or the robot here, so etc. For example, gripper geometry and pad coating pull test. So again, these are technical terms, I don't know exactly. Now when you talk about comprehensive and analytic is so it's more like that you build all the subsystems in a software and you integrate them together, and it's more like full dynamic simulation, where you will have all the component or subsystems and you try to simulate. And of course not all the discipline will going to have that kind of a way of doing things, and sometimes some discipline have the structured academic way of understanding that, okay, so this is the systematic way to go forward to harvest knowledge in a full dynamic simulation scenario. User interface hardware linked to dynamic simulation. I think it is this is again a very abstract takes to think of, but I can think of a good example here. One is actually the simulation, the flight simulation test, because there pilots are tested not on the original airplane, but you have to go to a room and you have to test, and that's also the real interface, hardware interface, where that will be used in an original plane, but then the rest of the things are simulated. So that's a comprehensive prototype, but analytic. Now that belongs to analytic, but something which is very analytic and very comprehensive, not generally feasible, because comprehensive by default means basically you try to incorporate every subsystem into the product. So if you are incorporating everything together, and so that generally comprehensive means something physical. So that's why it's not generally feasible. And let's focus on now this first quadrant, that is physical and comprehensive. So alpha prototype system integration, beta prototype field testing. So alpha and beta, these are terminologies that are used. We know that alpha version of the software, beta version of the software. I think beta is the next version maybe. And full scale foam model tested with new software and old model, system level drop trace. So these are technical term again, but you understand that it's now we are talking about more of a complete system where 2 or 3 subsystems had been incorporated into each other. That's why we are calling them comprehensive, but everything is now in physical form, not in some computer simulation in computer happening. So I think this plot is very interesting and we can learn a lot of things from it. And let's again, maybe this is a repeated thing that I'm doing, but let's again, because we are an academic committee, so that's why let's again go back from that point of view. If you see these things, then we realize that when we work on a bigger project, and we all have the pressure of publishing papers and maybe patents. If we can generate patents, that would be great for us. And then depending on in this way you build your CV. I mean, of course not for the job, considering you already have a job in university, or some institute, or even some company, but you need to build on portfolio. Otherwise you can't attract the money from investors or government organizations. So you have to think from a longer term point of view. And when you try to think from a longer term point of view, you need to have the vision that what after 10 year, 15 year, 5 year, 10 year, what's I want to see myself, what is the product that I want to build in my lab. Actually, maybe not the exact form of product, because research fields are now very segmented, and even if you do innovation in a very segmented way, that's also a good boost to your CV, that you don't need to go beyond that actually. But let's say for my point of view, I am more often interested into building a genuine product. I'm not content with just doing innovation in a very narrow structured sub-discipline. So that's my personal choice. So from that angle point of view, I feel like these are the concepts that I can always take a note from it, that how I plan my smaller part of the research. 6 months, this is the prototype, I want to focus on 1 year, I want to gain knowledge into that. Okay, so and very carefully I want to do simulation into this part of the subsystem and try to understand different changes, how it how performance changes, and then I move into other subsystem and try to see how different changes, different geometries affect the performance, and more importantly how different subsystem innovations that I'm trying to talk about basically when we try to bring them together, how they work actually. So that's also very important. So, and then of course, when you build some portfolio, like maybe a good number of papers, maybe one or two patents, then you are capable of finding, attracting some fund, that maybe government or private funds. And then you can talk about some physical prototype. Now we are moving from analytic, that means the below part of the plot here, to the physical prototype. And then we try to generally start with some small scale version of the instrument and try to see the performance. And then we move to more of a first quadrant. Then we try to bring different comp subsystem, and more we go into that direction, our endeavors become more expensive. And that's why it is very important that we try to take this understanding that the money is always a factor, and nobody will going to give you money, even if you are, of course there are politics happening, but in more in general sense, that money, people want to give money to you if they think that this investment is something will be fruitful in future. Even from a government organization, they want to give money to someone who produce some results, so from that angle, you want to take these steps very carefully, that starting from the bottom part of this pyramid, not pyramid, but the bottom part of the particular plot here, that you want to start with something analytic first. And so basically you start with the third coordinate, which is more focused and analytic, and you work on simulations and try to gather knowledge on certain design, certain thing, and what is the future, depending on the overall future of it, you try to gather knowledge. And then you try to create then you try to build the best simulation knowledge and try to make it more comprehensive. And then you try to go one step, and then so basically now I'm talking about going to the fourth coordinate, and then you move to the second coordinate, where you have some money and try to get certain physical prototype, small scale, and then you move to the first coordinate. So that's how we should look at it. Okay, so now we will understand what are the prototype used for. Of course, we know the answer in a general way, but let's again just look at the points like learning, communication, integration, milestones, and I'll just read it from the text itself, and hopefully we'll learn a lot of new things here. So within a product development project, prototypes are used for 4 purposes: learning, communication, integration, and milestones. Learning. Prototypes are often used to answer 2 types of questions: will it work, and how well does it meet the customer need. So in let me see. So so for this particular example, they come up with different design of the wheels, and for the impact test, and also in the development of the wheel design, the mathematical models of the spoke were analyzed to estimate the stiffness and the strength of the wheels. This is an example of focused analytic prototype used as a learning tool. Now, second topic or second thing that one can achieve from prototype is communication. So this is something more important for industry people, that prototypes enrich communication with top management, vendors, partners, extended team members, customers, and investors. This is particularly true of physical prototype. A visual, tactile, three-dimensional representation of a product is much easier to understand than a verbal description or even a sketch of the product. third topic that third thing that one can achieve is integration. Prototypes are used to ensure that components of and the subsystems of the product work together as expected. Comprehensive physical prototypes are most effective as integration tools in product development projects because they require the assembly and physical interconnection of all parts and sub-assemblies that make up a product. So one good example would be the aeroplane, and it contains a lot of different kind of systems, and you want a integrated system to check whether even the simple thing that whether everything fits well, and different things like whether the fact that subsystems are working well independently, but then when you integrate into the full system, because of the communication or interaction between different systems, maybe it will not work actually. So common names for these comprehensive physical prototypes are tested, alpha, beta, and pre-production prototypes. So it's not just about the physical products which are physical. It can be products which are software products also, like beta prototypes of software, etc. So there are also the coders integrate all their different part of the code together, and it's not just one people, different people's work together, and last thing is milestones. So, and again, this is important, I think, for more of an industry people, particularly in the later stage of the product development. Prototypes are used to demonstrate that the products have achieved a desired level of functionality. Milestones prototype provide tangible goals, demonstrate progress, and serve to enforce the schedule. Senior management and sometimes the customer often require a prototype that demonstrates certain functions before allowing the project to proceed. So, and in the table you can see that in the learning phase, basically all sort of prototype like focused analytic, focused physical, comprehensive physical are used. And as you go to the communication phase, in the or not phase but communication, if you want to achieve the communication goal, then mostly it is focused physical, not analytical, and comprehensive physical. And when you try to achieve the integration goal, then it's mostly comprehensive physical. And finally milestone, it's comprehensive physical. So yeah, so before that we understood that till now the previous to this slide we understood that what are the different kind of goals or not advantage but different thing you can achieve, like learning, integration, communication between the senior super management people, they need prototype, etc. Now we understand that here we all understand that several principles are useful in guiding decision about prototype during product development. So like which prototype we should go for, and that depends on the product and various other things. So first, of course, the principle is the analytical prototypes are generally more flexible than physical prototypes. So because an analytic prototype is a mathematical approximation of the product, it will generally contain parameters that can be varied in order to represent a range of design alternatives. In most cases, changing a parameter in an analytic prototype is easier than changing an attribute of a physical prototype. Second thing is physical prototypes are required to detect unanticipated phenomena. So now we understand. Now maybe I will just remind you back in some 2-3 slides previous to that, we are talking about something like that the simulation is important, but simulation also has limitation in a sense that there are a lot of things that one would expect in a real physical system that you are not anticipating in the physical simulation system or simulation digital twin. And the reason for that is not just because we don't understand the physics or geometry or something like that, but maybe sometimes it's unintentional also. Sometimes a lot of thinkings gaps are there, so that's why not the comprehensive but the focused physical prototypes are also important, very much important. That's why from an academic point of view, it means that you don't want to, after finishing all your simulation goals, simulation based knowledge gathering, you don't want to flip into a comprehensive model, because it is even not possible from a money point of view. But you want to start again from a small prototype, physical prototype, and scale it up and try to understand exist, and try to understand that whether your simulation knowledge that you gathered is reflecting into your physical system or not actually. So yeah, so in that context you stumble upon a lot of unexpected thing, that okay, so what we thought about a simulation model there, we understood that different thing like cost structure is one thing maybe, and sometimes different other factor also. So a physical prototype often exhibit unanticipated phenomena completely unrelated to original objective of the prototype. One reason for this surprise is that all of the laws of physics are operating when the team experiment with physical prototype. Physical prototypes intended to investigate purely geometric issues will also have thermal and optical properties. Some of the incidental properties of the physical prototypes are irrelevant to the final prototype product and act as an annoyance during testing. However, some of these incidental properties of the physical system will also manifest themselves in the final product. In these cases, a physical prototype can serve as a tool for detecting unanticipated detrimental phenomena that may arise in the final product. So yeah, so and also, so this is more, text is basically more about the industry people, but from an academic point of view also we understand that, like you studied a certain detector in a simulation model and simulation environment, you built your own design and different geometries, etc. And but when you go to the physical small scale physical prototype, then you all of a sudden realize that okay, so there are a lot of other factors that I haven't or modeled it in a idealistic way that is not true in the physical system. So yeah. Now this is very interesting. Again, the graph is here also is important, and that is again that that the question that we are, again just to recap, that question that we are trying to address is what is the good prototype, what is the relevant prototype for the current product development phase that we are in, or current research, academic research that we are doing, what kind of prototype we should go for. And of course from an academic research point of view, of course the software is the first part, not the software of the actual physical product, but the simulation I'm talking about. Yeah, but here you will understand that depending on the risk factor or technical and market risk and the cost high to low, you can choose different kind of prototype. You can so let's explain this graph here. So if the cost of the cost of making a comprehensive prototype is low, and if the risk of the product is low, risk of the product low means basically if you create a bad version of the product, that doesn't mean that you are losing a lot of money. So then one prototype may be built for verification. That means you can start doing the prototyping from an early stage. For example, printed goods, like maybe you are using a 3D printer to generate some mold of certain kind of a toy, new toys, and you're trying to test which mold will be good, etc, aesthetically, various other point of view, ergonomically, etc. So in that case you are allowed to do all sort of do all the prototypes in early phase. Don't wait for like mathematical design of something and try to integrate into this and try to, because that also takes time actually. So because the physical prototype also is always preferred, because you can always jump into the actual thing, how does it feel, and again it all depends on the actual product. Now if the cost of the comprehensive prototype is high but the risk is low, that means if the product goes wrong then you are not losing too much money. And the example is like commercial building and ships. Yeah, so then few or no comprehensive prototype built. uh, yeah, so in Europe, I think I know that a lot of buildings are basically not the owner made, but rather made by the companies, and most of the time you go into a certain road and you see that certain portion of the whole block, the houses are all identical, and that's because those are made by a certain company, and that the particular design or geometry or different choice or different window size, etc., all these decisions comes from some previous experiments, that is defined by some lot of different objectives, like aesthetics and engineering, and durability, and then of course the cost, etc. So there you can actually do certain prototype, or try to into this particular project. In this 10 buildings or 10 houses that we'll build, will look we can do this in this way, and that doesn't mean that those houses will not be sold. The customers already paid that, and they know that how that building will look roughly, but within your company you are actually making a lot of different kind of calculation, like how different objective, like how to reduce cost, how to make it durable, how to make it aesthetically good, etc., etc. So depending on all these objective, you try to build come up with different parameters, and different window size, different glass. I will procure the window from this company because the good, bad, etc., etc. So there you can actually, of course the cost of the comprehensive prototype is high, but it's not like if you make it a little bit wrong or not so good, doesn't mean that you again have to this up, and ruin sorry scrap the building and make it again. That is not the case. So that is one good example. And of course ships are also, you can always make a ship with certain design, etc., etc. Yeah, as long as it yeah, I really don't know the detail of it. But now let's move it to a technical or market is high but the cost of the comprehensive prototype is low. So then maybe I'm explaining it in different way. The y-axis should be, the risk is basically that it will going to fail, something like that, that whatever idea you are proposing, there is potential that because of the complexity it will going to fail. So for example, the answer to that is the software, because software is just within the computer and it's not so expensive to build. And if you are actually outsourcing this to like a country like India, where there are a lot of coders are there available, and different big companies, they are actually hiring Indian peoples to do code. Yeah, so there you can, so that is a high risk product, in a sense that it will, you build something and in the first phase itself it will be successful product. Not that case actually, because softwares will go through a lot of refinement. Consumer product, like even making a certain cosmetic products may go through different sort of trials and etc., etc. So that is a case of low cost for comprehensive product, but the high risk, because high risk in a sense that it's not easy to come up with a good solution in the first trial. We have to do reshuffle, etc. So yeah, and finally, if it is the cost of the comprehensive prototype is high and the risk is also high, then you focus on analytic prototype used extensively, careful planned comprehensive prototype. Sometimes first unit built in actual is actually sold. Okay, so for example airplanes, so there you can't really that okay, so let's build, oh no, this is not good, so scrap it up, etc. Satellites, you can't do that because it's so expensive. So you start, so again, I will just try to see from an academic researcher's point of view, and I think we can, what quadrant we belong. I would say that the uh, yeah, so I think I would say that it is the high cost and high risk, because you can't really yeah, so you can't really, you have to make the product or whatever the thing that you are building at least to a certain performance level, beyond certain performance level, otherwise there is no point of building it actually. So again you need to go step by step because it's a complex system. I mean, specifically I'm talking about my system, like maybe a medical scanner, because it has a lot of subsystems, softwares, hardware, and electronics, and etc etc. So you want to take it from an analytic point of view for software development. Software, not like the software part of the final product, but the simulation I'm talking about. So I think we belong to, most of the academic research belong to the right, upper right corner quadrant, where you want to take one step at a time. And yeah, maybe some research doesn't I think some engineering may not be that expensive. For example, I know from one of my friend, he works on smart window, etc etc, vs small IoT tools. So I hope the cost of comprehensive prototype is not high, low, and the risk maybe is high. That means he need to build an innovative product. That means he need to scrap a lot of things, so there he can really rely on many comprehensive prototype built. Yeah. Yeah. Okay, now we will talk about two general tools that is relevant to prototyping. I mean, relevant to the example that the author had given, and I think relevant to most of the people who are listening, is, or maybe not so relevant, but these are general tools, the the CAD design and 3D printing. So, and yeah, and of course what I'm trying to say here is that depending on your field or in your own expertise domain, the prototyping tools can be different. It can be some dedicated software used by your community, or it can be certain instrumental, the way that you test a certain instrument, various other range of things. But I think it depends on the specific field, and that's why you can't really cherry pick anything out of it. And so just as far as cherry picking is concerned, so we choose, and the author actually choose the CAD design and 3D printing. So CAD design is something that since 1990s, the dominant mode of representing design has shifted dramatically from drawings often created using a computer to 3D computer-aided design models known as 3D CAD models. 3D CAD models represent designs as collection of 3D solid entities, each usually constructed from geometric primitives such as cylinder, blocks, and holes. So this is important. The geometric primitive means, if you, because I remember that when I was looking into one CAD design of a certain instrument, so it's more like if you zoom it, you realize that it's basically it's a tessellation. Actually, tessellation is a how should I put it? It's a geometric structure. So they make the whole design. If you zoom it, it's basically tessellation. Actually, the units, the fundamental units are tessellation. So it's not like a analytically every thing is defined, like this is the diameter, this is etc. Not like that. So I don't know, I never used specifically for my research, but I know basic thing about that. So that's the primitive for that particular case, and that's why I'm saying it is important, the geometric primitive concept, that it's not like everything is analytic there. So yeah. So the advantage of 3D CAD design modeling include the ability to easily visualize the three-dimensional form of the design, ability to create photorealistic images for assessment of product appearance, and the ability to automatically compute physical properties such as mass and volume, and the efficiency arising from creation of one and only one canonical description of the design, from which other more focused descriptions such as a cross-sectional view and a fabrication drawing can be created. Through use of computer-aided engineering (CAE) tools, 3D CAD models have begun to serve as an analytical prototypes. In some settings, this can eliminate one or more physical prototype. So here I can give my example that in a lot of my softwares, the software that we use for simulation, there you can import CAD designs actually. So that is an example of CAD, computer-aided engineering, I would say. So in some setting, this can eliminate one or more physical prototype. When 3D CAD models are used to carefully plan the final integrated assembly of the product and to detect geometric interference among parts, this may indeed eliminate the need for full-scale prototype. For example, in the development of Boeing 777 and 787 jets, the development teams were able to avoid building full-scale wooden prototype models of the planes, which had historically been used to detect geometric interferences among structural elements and components for various other systems such as hydraulic lines. Using a 3D CAD model of an entire product in this manner is known, depending on the industry setting, as a digital mock-up, digital prototype, virtual prototype. 3D CAD models are also the underlying representation for many types of computer-based analysis. Forms of CAE include finite element analysis of thermal flow or stress distribution, virtual crash testing of automobiles, kinetic and dynamic motion of complex mechanisms, all of which have become more sophisticated every year. In pegboard, development engineers pegboard, basically here is the example of the author had taken for this chapter. Development engineers conducted finite element analysis of structural integrity to understand impact stresses at various drop and crash angles. So yeah, and here in the slide you can see, of course, the image that I have taken from internet. This is some sort of image engine of certain automobile maybe, and so this is a CAD design, and you can see, and in fact you can disassemble all the things, and you can make a physical prototype by 3D printing certain parts or full, of course not certain full part. I don't know whether it will be useful or not, but yeah, maybe I'm just saying as an example, but maybe this is not the case in this particular case, but maybe in other cases the 3D printing turn out to be important. I mean, what I'm trying to mean is that maybe for engine 3D printing may not be so this is not my field certainly, so I don't know. Now another tool that is generally used in most of the cases is 3D printing. And before I forget, I want to say that there is something called additive manufacturing. I made a video long ago. So what I understood, and I think it's very general thing, not like in absolute very interesting thing, but it's not just 3D printing is not just used for prototyping, but it is also used for manufacturing nowadays. That a lot of like prosthetics and medical equipments are can be made through additive manufacturing, that means 3D printing, and the different choice, and it's a fast moving field, and different choices of the material and different techniques had been developed. So But today, of course, we are talking about 3D printing in terms of prototypes. So where it means basically that you build certain part of the system and for the certain kind of specific testing, like in this particular example for the particular chapter, we are talking about, let's say, maybe you design the wheel of certain design of and test on a independent setting. So yeah, so in 1984 the first commercial free-form fabrication system was introduced by 3D Systems. That's, I think, is a company. That this technology called stereolithography, and dozens of competing technologies that followed it create physical object directly from 3D CAD models and can be thought of as 3D printing. This collection of technologies is often called rapid prototyping. Most of the technologies work by constructing an object one cross-sectional layer at a time by depositing a material or by using a laser or selectively solidifiers liquid or powder. The resulting parts are often made from plastics, but other materials are available, including wax, paper, ceramics, and metals. Yeah. In some cases, the parts are used directly for visualization or in working prototypes. However, the parts are often used in patterns to make molds or patterns from which parts which with particular material properties can then be molded or cast. Three-dimensional printing technologies enable realistic 3D prototype to be created earlier and less expensively than was possible before. When used appropriately, these prototypes can reduce product development time and or improve resulting product quality. In addition to enabling the rapid construction of working prototype, these technologies can be used to embody product concepts quickly and inexpensively, increasing the ease with which concepts can be communicated to other team members, senior managers, development partners, or potential customers. For example, pegboard prototype shown. So let's forget that. So that's all about 3D printing, and here you can see in the image, I think they are using some ceramic or maybe, I think, metal, and making some prototype of certain part of something. So yeah, that is a 3D printer of certain kind. Yeah. So that's it all about the video. And so there are certain extra thing in this chapter that you can read it from the book. That the link, of course, is this, as we always talk about in end of the video. This is the downloader and this is the name of the book we are using to make this video. And there are certain part of the chapter, end of the chapter, I skipped because I thought like those are not important for us, but if you think, you can read it. And I think that topic is basically more about planning for prototype, like how do you plan the prototype, step 1 would be like define the purpose of the prototype. Step 2 would be establish the level of approximation prototype. Step 3 would be outline an experimental plan. Step 4 would be create a schedule for procurement, construction, and testing. So these are the things, but I think maybe that these are not so important for me, and doesn't seem like, so that's why I skipped it. But you can read it from the book also, of course. And so as usual, this is the link and the name of the book from where we are making the video. And if you like the video, please like, share, and subscribe. And that's it about this week. I will promise that next week I will, of course, upload another video on some different topic, and hopefully maybe on the same topic, continuing in this lecture series. So yeah, take care. Bye bye.